Introducing Ultimate Tester. This is a project I was working on over the last few months. It can test a variety of electronic components like resistors, capacitors, inductors, diodes, MOSFETs, transistors. It can also supply one with a variety of voltages, anywhere from 3 volts to 15 volts, which is adjustable using this potentiometer. It has the ability to provide voltage or current through a battery or through USB. It has battery protection feature. It has circuit protection feature in terms of an electronic fuse, which has under voltage and over voltage protection. It can supply up to 1.5 amps of current, and also has a feature to limit current which is going out using a jumper here. One can select 0.5 or 1.6 amps, and it can sense current as well. The USB auto select feature is like this. If one connects USB, it directly switches to USB voltage. We can see here VIN is 4.95. If I remove this, then the battery would be used. The battery is a Lithium Polymer Battery. It can supply up to around 1.2 amps. If one is using only the lithium-ion battery, then the max current would be less, up to like 800 milliamps or 1 amp based on the voltage one has selected. It also has a battery charging feature, so the battery can be charged directly by using USB voltage, and it's in a small form factor of an Arduino Uno. It's based on the same box, which is of same case, which is of Arduino Uno. So I wanted something small, pocket-sized, which can test a variety of components and also provide one with different voltages and a good amount of current. I call it Ultimate Tester. It's a combination of two projects. One is Lithium Polymer Battery Charge Boost Protect circuit, which is on the left side, and an open source hardware project called Component Tester, which is on the right side. It also has a flashlight, which is basically an LED, which I turn on using a MOSFET, and I've added a lens in front of it, so it gives some nice focused light. I'll show the PCB. The PCB is, as mentioned, divided into two sections. On the left is LiPo Charge Boost Protect circuit. On the right is Component Tester circuit. I've made it a one-sided PCB, except one IC which I added towards the end. The LiPo Charge Boost Protect and Component Tester circuits are separated, so there's it's nice to not have interference from higher voltages. Also, if one wants, one can just break these and use the separate boards separately, the two boards separately. I provided good thick traces for high current paths here, and good planes, like big enough planes for heat dissipation from the electronic fuse and from the battery protection IC. I'll show the PCBs on an open board. On the left side is the LiPo Charge Boost Protect PCB. This PCB has been greatly influenced by Great Scott's LiPo Charge Boost circuit. That PCB did not have USB feature, which I wanted. So I wanted an option to use USB voltage, and also it has headers. So if one wants to directly use USB, one can use these two headers. If one wants to use 5 volts, 5-volt header is also there. It can only supply 200 milliamps. Then if one wants to use V out, which is one's own desired voltage, so V out is like 6 volts here. So one can, using this header, one can choose what voltage one wants. So V out, we can see, is 9 volts, 7 volts, 6 volts, 8, 9, 10, up 12, 14, and now the protection starts. So above 15, it has the electronic fuse cuts off the voltage. There are in-circuit header jumpers. So one is here. This is for the 5-volt LDO. The 5-volt LDO powers the component tester circuit. So if one is just testing out something, one can just remove this and only have the LiPo Charge Boost Protect circuit active. One can also disconnect this jumper, which is before the electronic fuse. So only up to the boost circuit output would be there, and electronic fuse will be disconnected, and V out would not have anything. There are other test points as well. I'll show on the PCB. So V boost, ground. There's an IMON, which I don't see a lot of use, but I have added it. IMON is for monitoring how much current is going out from the electronic fuse. Then V out headers, 5-volt headers, test points, VIN test point, battery always on test point. There is also one more test point called power switch. So it has the functionality to automatically turn itself on and off. So if one presses this, battery would be connected to the whole circuit, and if we turn it off, the battery would be disconnected. On the right side is component tester circuit. The component tester project is an open source hardware project. It's a really nice and very well documented open source project. It has schematics as well as readmes about a variety of things one can do, or what it can do. It's based on an Atmega circuit. I have one non-working board as well. So the Atmega microcontroller. Yeah, so this is a Atmega 328P microcontroller. So the component tester circuit is based out of this. On this, it uses two resistors, 680 and 470 kilo ohms, on 3 test points to judge what the component is. So it's pretty nice. It has ESD protection diode. So if there's a charge electronic component like a capacitor, someone puts in by mistake, it will protect the microcontroller. And it also has other protections like 5-volt TVS diode. Yeah. I basically did this project to learn PCB design. I had not designed a circuit before designed a PCB before, so that was pretty nice. There's one mistake which I did, or modification after completing the PCB. This is the current sense IC. Earlier I was running it using the microcontroller's bar, but I saw a microcontroller does not supply a stable 5-volt. It supplies anywhere around 4.8, 4.7 volts. So I directly connected it to the 5-volt. Now it gives us quite stable output. It's based on Hall effect. It works quite well, but to be more accurate, maybe INA 331 or 221 ICs, those would be better. The component testers project has a rotary encoder which one can use to cycle through the various options. I have a few components here which we can test out and see how accurate the component tester circuit is. It gives 198.9. This is a 100 ohm 1% resistor. Let's see using a multimeter how much is it. Using multimeter is not quite easy, so that's why I wanted something like this. So 99.65, so fairly close to what the multimeter is saying. This one is a larger one. To 19.8 kilo ohms. To 21.15 kilo ohms on the multimeter. So again, fairly close, very accurate, like quite accurate. This one, I think it should be 4.7 kilo ohms, so 4711. 4.69. So again, fairly near, like quite accurate. Then I have a capacitor. It's a film capacitor around 330 or 350 nanofarads. So it's saying 320 nanofarads. And a good thing is, a nice thing is that it gives you the ESR resistance of the capacitor. Let's see. Oh. So multimeter finds it to be 316 nanofarad. So very near, extremely near to what the multimeter say or finds out. Okay. It can also do small, like up to like 50 or 100 nanofarads. Yeah, or I think picofarads also it can go. Let's try this. This is a BC547 PNP transistor. 547, so NPN BJT. So it gives you what the component is. So just by using this, one can know what kind of transistor is it. So BJT NPN. So it also gives the leads. So CBE. So CBE. It gives the gain value, gives the base emitter voltage, gate voltage, and yeah. So basically, using this, one can have a fairly good idea of what the component is, and many a times not look at the data sheet. This is a MOSFET, so 2N7000. It accurately finds out that it's a N-channel enhancement mode MOSFET. Nice thing is that it gives you the gate voltage almost 1.9 volts, the gate capacitance 31 picofarad, the RDS resistance 2.85. I think the data sheet gives anywhere from 1.5 to 5 ohms. So very accurate. Just using this, one can know what the RDS value is, or the gate capacitance and the gate threshold is. So yeah. I think besides that, it has a PWM feature, so that's pretty nice. I don't have an oscilloscope here, but we can see the PWM using a diode. So let's see that. So it's saying on 2, let's put that. And if I reduce the frequency by a lot, then we would be able to see the PWM. The camera is running at 30 frames per second, so I'll reduce it to, let's say, at 30. Okay, 30 I'm not able to see on the camera, so let's say at 5. So at 5 we can clearly see that the PWM is working well. I had seen on the scope it gives really nice outputs. So if I increase it, we'll see more white and shorter dark times. If I reduce it, then small blinks. So pretty nice feature. Besides that, square wave, then logic probe. Logic probe can be used to know the voltage of like between 0 to 20 volts. So we can directly just see it here itself. So V out is around 6 volts, so 6 battery voltage 4.05 volts. What I've added on this is the VI measure. So using this, one can know what the output voltage is, and using current measure, one can sense the current, how much is going through that wire, and it also gives a power output. So power output is just a multiplication of V out and I sense. So let's see that. Right now it's running on battery power, so it should be able to supply around 1 amp at 6 volt. So we'll just have a look. So 1.17, and multimeter reads it as 1.12. So fairly near, and that's a lot of current. So all this current is just through the battery, lithium polymer battery. If one uses a bigger battery, then more current can be supplied. And using USB voltage, one can supply even higher current, up to 1.5 amps. So I'll add one more 10 ohm resistor in parallel, so it would be around 2 ohms. But there are other resistances of the wire, so it becomes higher. So let's see this. So now it should reach closer to 1.5 amps. So 1.4. So that's, and yeah, V out has not dropped quite by a lot, like it's 5.6 volts. So pretty nice, pretty powerful small device. Yeah. We can just have a look at the various LEDs on the project. So there's a yellow color LED, which is for USB. I can actually show it on the open one. It would be nicer. Open. So yellow one is USB. Blue one is battery charging. There's a battery charging IC, which charges up to 4.2 volts. Then the green one is whenever this is on. There's a red one as in Great Scott's design. It's the same design, same circuit. If V out is above like 8 or 9 volts, then it lights up. So here we see V out is 11.5. So if I reduce this, then LED will turn off, start turning off. So at 6.5 it turns off. At higher voltages it turns on. Yeah, goes up to 14.5, 15. Yeah, after that it will just turn off because the electronic fuse will cut off things. So here, and right side is a fault LED which I had added. That's also something different from Great Scott's PCB. So it's the same IC but a different version. And another nice thing on this is that there's no latch. There's also the electronic fuse will provide short circuit protection. So if I connect V positive and negative, so this would be short circuit. It will turn off everything, and fault has turned on. So now there's no latch. So there's no retry, so one will have to disconnect things and again start it. So I found it like auto retry I didn't want that, so this is pretty nice feature. Yeah, and there is auto on, auto off. So as there's a 3P ST 3-pole single terminal slide switch here. At the bottom it would be on software on. At the top it will always be on. So if one wants to just use this side of the board, one can just turn it on and off from the top. At the center it's off. So at the center it's off. Yeah. This switch is for selecting what the Vout would be. So right now Vout is 13.4 because using the potentiometer I've chosen that. So Vout is 13.4. If I put the switch on the left side, it's a constant 6 volt. So that's yeah, that's for selecting that. Let me talk about the left side of the board. So after USB and the battery, so after battery there's a battery protection IC, and after that is a load switch. So the load switch will either cut off the battery or connect it to the circuit. So whenever we press this, the load switch will turn on and let the battery voltage be on the other side, come on the other side. It will also always turn on whenever we connect the USB. Next to the load switch is battery charger IC. It will charge the battery. Yeah. There's a common cathode double diode here. So whenever the user presses this button here, or whenever the USB is connected, it will turn on the load switch, and that's how it starts. After the load switch is the battery, the boost IC. This is MT3608 IC. After the boost is electronic fuse, and after electronic fuse is 5 volt LDO, and that goes to the component tester circuit. Let's talk about the PCB. So basically I did this project to have something nice, small, pocket sized, a powerful tester. It can give voltages, whatever voltage user wants, with up to like 1 amps of current, which is quite powerful, and it's pocket sized in the form factor of Arduino Uno. I basically did this to learn PCB designing. This was the first project which I did which had a fully designed PCB, and there were quite a things to learn. This was my third PCB for the project. The first one was two-sided one, hand soldered, and it had some schematic mistakes, so it did not really work well. The second one worked, and yeah, it worked quite well, but it had one mistake on the pins, so I could not have the PWM function, and also it did not have a voltage option to provide different voltages. I was powering it using another board, a boost board, so that worked quite well, but I wanted something fully in on the PCB, not use another board. So after that I designed this one, and the second one was also two-sided, and I figured it takes quite a bit of time to hand solder everything. So the third one, this one, I designed one-sided, and it has nice thick wires, traces, up to I think 50 to 60 mils width, and the spacing is also I think minimum 10 mils, and so it should be quite safe. And I designed it of one-sided, and I got a hot plate, a pretty small one. It uses USB PD power and runs up to at 20 volts, and within a few minutes, like 1 minute, it's able to reach 150 degrees Celsius. And I use a stencil as well, and using that it was fairly easy to solder it. Removing the splits or bubbles of solder was a bit like time consuming, but maybe using a better solder paste that would solve that issue. Yeah, but was quite interesting, and now I know how to design a PCB, so that will come handy in the future. And yeah, I'll include everything on the post, so if anyone wants to use this PCB or modify it according to their wishes, they can. Yep, that's it. Ultimate Tester.